Welcome to lecture SP7, our seventh lecture, and in this lecture we will continue studying Poisson process. A Poisson process is a process where we have arrivals. There is a small recap. We have arrivals at the rate of lambda arrivals per unit time. The time can be divided in various chunks or intervals, but the arrival rate in each interval remains the same, and these time intervals can be of variable length. And secondly, we studied that it's a memoryless process. This means whatever has happened before time interval t, the thing that is going to happen during time interval t is independent of that, means it's independent of the past. Today we will talk about modeling inter-arrival time. Inter-arrival time is the time between inter-arrival time is the topic for today. It's the time between two arrivals. Suppose an arrival happens at time t. What is the probability that the next arrival takes place after this time, after a given time? So inter-arrival time is modeled using a probability distribution that we call exponential distribution. That we call an exponential distribution. This distribution, exponential distribution. Exponential distribution was studied by us in undergrad in various subjects like probability and stat, for example, but maybe in some other subjects too. Right, it's a continuous distribution as opposed to Poisson distribution and Bernoulli distribution. It's not discrete, it's continuous. On x-axis we have this x, which can be time. In most of the cases when we talk about Poisson process, this variable we replace it with time, small t, and the only parameter of this Poisson of this exponential distribution is the rate of arrival, lambda, the same as we used for Poisson distribution. And the PDF of this distribution is lambda times e to the minus lambda x, where x is defined only for where the probability distribution PDF is defined only for positive values of x. It's not defined for negative x. If we draw it, it's like a decreasing exponential, and it is in fact a decreasing exponential, but since it is a distribution, a probability distribution, integrating this expression from 0 to infinity should sum to 1. You can verify it at home, that integrating this from 0 to infinity will give you a 1, no matter what the value of lambda is. For all values of lambda, it will give you an answer. Of course, for positive values, because arrival rate is always positive. For all positive values of lambda, this whole expression will always be integrated to 1 from 0 to infinity span. The expected value of this distribution is 1 over lambda, variance is 1 over lambda squared. You can verify these values from the basics, from the basic expression for the expected value and variance of our distribution. Expected value of x, we have studied in modeling and simulation course and in undergrad that expected value of x is, since it is a continuous distribution, expected value of x would be integral from 0 to infinity x times probability of x times dx. You already know that. And for variance of x, we have expected value of x squared minus expected value of x whole squared. So you can verify these expressions at home. Right, let's move on and solve an example related to exponential distribution, where we have an average length of a phone call received somewhere is 10 minutes. This means the rate is, of course, the rate is something happening per unit time, arrivals per unit time, or some event happening per unit time. So it has to be 1 over something because it's a rate. Given the length of a phone call is exponentially distributed. So we are given that the length of calls is distributed as an exponential random variable. F of t can be written as lambda. We have just studied the PDF is, now we have replaced x with t, since we are studying it in the perspective of a Poisson process. So it's obvious to have a t here. So this is lambda, where lambda is 1 over 10, e to the minus lambda t, where lambda is 1 over 10 t, and this all is defined for t greater than 0. We already know that this probability distribution is defined only for positive values of t or independent variable. So in first part of the problem, we have to find the probability that a phone call is the duration of a phone call is less than 5 minutes. This means this is the plot where it is plotted as f of t, and this positive value would be 1 over 10. This positive value would be this value. This max value would be 1 over 10, because this is lambda in case of an exponentially distribution. So this value is 1 over 10, and this time is 0 time. So the probability that a phone call is of less than 5 minutes duration means we have to integrate this area between 0 and 5. So the area under the curve during this span 0 to 5 would be probability of t less than 5, integrated from 0 to 5, 1 over 10 e to the minus t over 10 dt. We solve it using the knowledge of elementary classes, and we reach to our probability 0.39. In part B, the second part, we have to find the probability that a given phone call is between 5 and 10 minutes duration. It's greater than or equal to 5 minutes and is less than or equal to 10 minutes. This means we have to integrate this much area, the area from 5 to 10 under this curve. Right, so integrating this curve from 5 to 10 would be the limits of the integral would be 5 to 10. We'll put the same expression in once again, and we'll solve it using our basic knowledge, and we reach to this value. Probability of that a phone call is between 5 and 10 minutes duration is 0.24. That's all for this lecture, and in the upcoming lectures we will be studying more about distribution of inter-arrival times, and we'll talk about independence in Poisson processes. Thank you.